Welcome everyone. In the interest of moving the class forward, I've developed this online lecture to provide the information for the lectures that we might have missed along the way. So first of all, we're planning on having our quiz next week. Quiz number 1 will occur next week on Wednesday. In order to prepare for that, I would like you to reread chapter 1 and to revisit the notes that we've had thus far in class, including these lecture notes today. You've been assigned homework 1. Normally that homework would be due next Tuesday, but this particular lecture I'm going to extend it to Thursday. This is for the spring of 2018 only. So continue on with your work over the weekend, and let's move on with the lecture materials. We've talked a lot about the differences of language and skills and basic thermodynamics for the class. So let's start out with that idea of the system, the boundary that defines the extent of the system, and the surroundings that occur beyond it. Remember, you've got to keep your eye on the ball. The ball is the system for doing the math and all the energy and mass balances for our systems that we're talking about. Feel free to pause this video anywhere along the lines to take some additional notes or rewind. Just a little reminder. So a system has basically these energy addresses or energy and entropy addresses that we call states. So the term state is the energy address of the system. Keep your eye on the ball is the system. States are basically functionally described by coordinates, these properties, values that are either measured or calculated that we would call properties or variables. And we're used to calling these state variables. So temperature, pressure, the V with a hat is specific volume. The N stands for moles, so the number of moles of constituent K, whether that K means oxygen or nitrogen. And they all functionally come together into our first state function, U, which is internal energy. So a state function is an energy address. A state function is a function of state variables. And so we have an energy address described by state variables. We're going to start off by talking about 3 system constraints that are pretty fundamental to thermodynamics. And those are basically determining how or whether or not the system allows energy and or matter, mass, stuff, to transfer across the boundary. So let's look at that first one. The first one is the most common system that we have. Ubiquitous systems all over the universe are open systems. An open system means it's a system where mass and matter, electrons or air or water vapor or others are exchanging across the system's surroundings boundary. So I have matter exchange and I have energy exchange across the boundary. That's the definition of an open system. So your human body could be described as an open system. The tree could be described as an open system. A photovoltaic module could be described as an open system because electrons are leaving the system and then re-entering the system after doing work. So the next one is, what happens if I just decide that I will model a system that essentially has no matter exchange across the boundaries? So stuff cannot exchange across the boundary, but energy can. These don't happen very often in fully functional systems. As I said, most systems are open, but we can use the closed model to describe systems that more or less function in a closed way. So Earth, as a planet, is in the void of space, and for the most part, there's not a lot of matter exchange. We're really only exchanging light, radiant energy, coming from the sun and in the shortwave form, and emitting longwave light out into space, and very little matter exchange occurs. Another example would be a thermos, an actual coffee thermos or a tea thermos that insulates, and if it's closed and we're not pouring liquid out of it, we're talking about something where only a slow exchange of heat is happening, but matter doesn't exchange across the boundary. And then, of course, the third one is an isolated system. So open, closed, and isolated. And an isolated system is where the constraints are modeling a system that essentially has no matter and no energy exchange across the boundary. It doesn't really exist in a really pure form, but as we've been trying to frame in class, there are functional models that allow us to really look at the balance between system and surroundings and do some calculations. And we will be using isolated models in the near future. So we have three system constraints. Constraints are basically the things that the system can and cannot do. And the three main system constraints that we're talking about are matter exchange and energy exchange. So once again, an open system, this happens all over our engineering programs in energy and mineral engineering, inside of energy engineering, inside of petroleum and natural gas engineering, mining engineering, environmental systems engineering. All of these are talking about open systems where matter and energy cross the boundary. Okay. But again, we'll be talking about closed and isolated systems quite a bit because we can learn a lot from systems that are more constrained, and we approximate or simplify a system as closed or isolated to functionally kind of get a better understanding of the way things work. Right? Okay, let's move on. I'm going to bring you to section 1.4 of chapter 1. This is Koretsky, page 15. The section on equilibrium. It's one of those things where I'm trying to draw your attention to a topic inside of the reading because the term equilibrium can be really glossed over quickly, and you can think you have a sense of what's happening, but without actually going deep into what is the functional meaning of equilibrium. Now, equilibrium refers to a state, the energy address again, that neither changes with time nor has a tendency to spontaneously change. So you have no net driving forces. So if you think in terms of physics and chemistry, driving forces lead to spontaneous changes. A system at equilibrium does not have change with time, but it also doesn't have a tendency to spontaneously change. A system that has mass exchanging across the boundary cannot be at equilibrium. Now, so that means that an open system where mass is being supplied or removed from the system cannot be at equilibrium. Your body cannot be at equilibrium. You are talking about non-equilibrium systems. Combustion of a fuel in an engine cannot be at equilibrium. Now, equilibrium, functionally in thermodynamics, will only occur in a closed system. Again, that's a system where there is energy exchange across the boundary, but no matter exchange. So let's look at a really general open system, which is a leaf. And it is both an open system and it is a non-equilibrium system. Now it's non-equilibrium because we have matter exchange going across the boundary of a leaf. So let's draw that. So I'll have the sun providing photons. The sun itself is a high temperature body, about 6,000 Kelvin. And then the sun itself is going to be shining light on a sunny day onto a leaf. The leaf itself is going to be at a temperature about 300 Kelvin. And let's draw a system a boundary around that leaf system. And we see we have two very different temperature bodies that are going to be working in relation to each other. We'll draw the sky around the leaf itself, and the air in that sky is roughly going to be the same temperature as the leaf, around 300 K. Okay, now the point here is that the light is going to be shining. There's a driving force from that very, very high temperature sun where the photosphere will deliver photons, and we'll call those photons reaching Earth as irradiance. And that irradiance causes a driving force in the system. Now remember, equilibrium has no net driving force. Here we have light as a driving force. That driving force basically says that we are asking, are we in thermal equilibrium between the sun and the leaf? No, because the temperature of the air is not the same as the temperature of the sun, which is not the same as the temperature of the leaf. And so we functionally do not have thermal equilibrium going on here. However, if I look at the chemistry of the system, and and I think about chemical equilibrium, well, how does that work? Well, I'll have moles of carbon dioxide, moles of water vapor going in and out of the system, oxygen leaving the system. That doesn't sound like equilibrium either. It sounds functionally like we have matter transfer going across the boundary, flowing based off of evapotranspiration and photosynthesis. And that is its own, that matter flow becomes its own driving force. So chemical equilibrium, no. However, between the air and the leaf, are we at a equilibrium of the variable of pressure? Now that's interesting. Well, actually, the pressure inside of the leaf and the pressure of the ambient air surrounding it is roughly the same. So we have a pressure-based equilibrium, but we don't have a total thermodynamic equilibrium. So you can have equilibria of certain variables without having a total thermodynamic equilibrium. Now I'm drawing a squiggly line with a squirrely d w prime. That's that inexact ordinary differential for non-mechanical work. And essentially what's happening is, as the sun shines on the leaf, we have photosynthesis, shines light on the leaf, and we have photosynthesis from the leaf. We will produce non-mechanical work, generating sugars, flowing out of the system. The convention for something leaving a system, based on our standard convention discussed in class, is a negative flow of energy. Similarly, we'll have heat flowing out of the system, thermal energy that is not related to this non-mechanical work, related to both the temperature of the system and the change in entropy. That heat dissipation also is negative because it's flowing out of the leaf system. In these non-equilibrium systems, they're very common. So non-equilibrium open systems happening all over the place. The leaf is just a very simple example of non-equilibrium systems, but just showing that it's really a common feature. So open systems versus closed and isolated, we tend to encounter far more open systems in class. Okay, so when I left off last week, I was talking about temperature. And I told you the definition, the mathematical definition, those 3 lines that you're seeing is a mathematical equivalency. So what we know as temperature is mathematically defined as a partial differential of internal energy relative to entropy. So partial differential of U with respect to partial differential of S. When I am holding 2 properties constant, that would be a constant volume system and a closed system, where n is constant, that incorporates a closed system. Temperature is an intensive value. You can split a room in half. The temperature will be the same in the 2 halves of the room. It's an intensive value. But let's explore that a little bit, because most of us, when we think of temperature, we think of temperature as being something that is more or less hot. Whereas, in fact, what we're measuring is the property of the way that a fluid either expands or contracts in volume because of a temperature change, or the way that the conductivity of a metal junction has more or less resistance, more or less current, when the temperature of the surrounding air changes. These are all changes in properties that are being calibrated to what is actually temperature. So if I flip temperature, because this is a partial differential, I can flip the partial differential to the opposite way, and 1 over T will be the partial change in entropy with respect to the partial change in internal energy. Curious thing about this is that 1 over T is basically as a rate of increase of entropy with respect to a change in internal energy. So how does the spread, how does the distribution of energy, which is called entropy, change with respect to the total amount of energy changing in the system? That's 1 over T. We also will use that. It gets a special symbol called beta. But that 1 over T relationship, you're going to find mathematically throughout thermodynamics and physics. It's all over the place. We have so many equations where the T of the function, the temperature of the function, is in the denominator of key equations, like the Clausius-Clapeyron equation for the vapor-liquid equilibrium, the the Arrhenius equation, the Van 't Hoff equation. These are things that will come up in our future studies as engineers, but I'm just letting you know you'll find 1 over T quite often. And here we're seeing it in the Maxwell-Boltzmann distribution. So this is the distribution of speeds of molecules, gas molecules, where the system is found at different temperatures. We've seen this in Chapter 1 reading, this plot that you're seeing right now. That function, the way that that curve is described as kind of this kind of humped shape with a long tail at higher temperatures, is described by the function of the energy distribution, which is 1 over A exponential to the E divided by the Boltzmann constant, KB, times T. So there's a 1 over T, an inverse T, right in the Maxwell-Boltzmann distribution of the speeds of energies, the speeds of molecules and their fraction within an entire gas sampling. So another way to look at this, like you see in that plot that 300 degrees Kelvin, or 300 Kelvin, is a much more tighter, it's a tighter distribution that's narrower than 1000 degrees Kelvin. Both of these plots have been normalized to a fraction of 1. So even though in reality the 1000 Kelvin would be a much larger curve, when we normalize the distribution to 1 and we integrate under the curve to get 1 in both plots, it would appear that the 300K distribution is higher, when in fact what we're really conveying is the tightness of the distribution, the entropy change. So let's look at what that breaks down as. So I could roughly, very, very roughly, think of temperature as the ratio of the partial change of integrated energy under the curve relative to the partial change of the dispersion of energy, the spread of energy for that same curve. And a lot of the way that we write this is potentially temperature is, as a way of thinking about it. Now, this is very generic. The mathematical definition is really what we're looking at. The incremental change in how much energy relative to the change in the spread of energy is what we're talking about when we're talking about temperature. And this stays within the class of thermodynamics and related science and engineering courses. This is not the way that we would normally talk about temperature with our aunts and uncles and family members. But inside of the science and engineering space, this is what temperature means. Temperature does not mean the speed of a gas molecule, because not all materials that we interact with are gases. Much of the time we're dealing with liquids and solids. Inside of the solar field, we're dealing with photons, which have no mass, and so have no functional speed the way that we would think of the speed of a gas molecule. So I want you to think about those things as you move forward. That temperature is quite a unique, the mathematical definition of temperature is quite unique, and it links together energy and entropy. And that's really a fundamentally amazing thing about a single property inside of the world of thermodynamics. If temperature is this complicated concept of partial change of energy with respect to partial change of entropy, but yet we have a societal norm of measuring temperature, well, what we're doing is we're actually measuring another physical property to get to code break our way to what is temperature. So we're measuring changes in electrical properties in materials, optical properties, if I were using an infrared camera, and I'm calibrating those changes in those properties of electrical, optical, volume-based changes into a scale that can be set at an absolute scaling, such as the Kelvin scale, to ultimately tell us what temperature something is. So we know that many fluids have basically a discrete volume change per increased temperature, or a change in pressure with changes in temperature. Very common old school thermometers are fluids expanding inside of a constant volume, a closed system with a constant volume. That would be like your standard mercury or the red liquid thermometers before. So let's look at this and let's use this idea inside of kind of, we'll call this beginner's code breaking, where I said that thermodynamics can be used for code breaking when we have intensive variables. If you refer on page 13 to equation 1.19, you'll see another writing of the ideal gas law. This is the ideal gas model, the equation of state for an ideal gas, where pressure is equal to nRT divided by volume, extensive volume. I could rewrite that where temperature is equal to pressure times volume divided by moles in the system times R, the natural gas constant. As a reminder, I'll have you take a look at table 1.1. You can pause this and go back and look at table 1.1 to make sure that you're using the right units in terms of the gas constant R. Always an important thing when solving problems. All right. So in our next lecture, we're going to be talking about the state postulate, where we are code breaking with intensive properties. We'll be talking about the Gibbs phase rule and this concept of quality. So stay tuned for that. Keep an eye out for that. I may even have a YouTube video to share on that topic as well, to keep you going on your homeworks as they're coming up. So be well, have a great day, and take care of yourselves out there. See you later.